Okay, so hello, welcome back to Hafsa's Math Academy, guys. This is the part 3, I think, of exercise 2.2 of the first year book. So let's just get straight into it because let's just do this. So as you can see on my screen, I have question number. We're gonna start with question number 7 because that's where we left off yesterday. And I have the solution along with some of my notes alongside. Today I am more prepared. I've actually gone through the notes before sitting down to teach them, and I wrote my own things as well, so it's easier to understand. Okay, so let's just start. Question number 7, if you look on the left side, I have your book, and if you look on the right side, I have my screen. So on the left side, it says, if matrix A equals to this, then part 1 is prove that for all positive integers n, the matrix A raised to the power of n should equal this big concoction that they've given us. So I'm just going to zoom into my screen, and you guys can see the question. This is the given formula that they've given us to prove. I've highlighted each of the elements of the matrix separately because it looked a little bit confusing before. So the blue is a different matrix. Sorry, the blue is a different element. The green is a different element. The red is a different element, and the yellow is also a different element. Now, basically, what this question is asking us to do is suppose n is any positive integer. It could be 1, 2, 3, 4, 5, 6, 1,132. When the matrix A is raised to the power of that integer, the answer should be of this structure that they've given us. It should be of the structure. So in this question, we're just going to prove a couple of examples. We're going to prove a squared. We're going to prove that a squared is compatible to this structure. We're going to prove that a cube is also compatible to the structure, and I think there's one more, but if there's not, we'll just figure it out. So yeah, let's just get started. Now over here, I just wrote for example, if n equals to 5, if our positive integer is 5, then we have to, multiply a 5 times. So it's a raised to the power of 5. We'll be solving for a raised to the power of 5. That's basically what they're showing here in that first line, in case it looked confusing. So we're gonna start off with a squared. So a is raised to the power of 2. To calculate a squared, we obviously have to do a into a. Now, by calculating that, the answer that we have in the end is just supposed to meet this structure's, requirements, or look, or whatever, So a into a, our given matrix is this, and we're just going to times that by each other over here. Obviously, they've multiplied all of it, then you further solve it to become this. Okay, this part over here, they've just taken y common to become x plus 1, as you can see over here. I'll erase that because my screen is looking very messy already. Now, you are probably looking, that's our answer to, no, come back. That's our answer to a squared, so a raised to the power of 2. Now you're probably thinking that does not look like the structure at all. Over here, the structure for this y element is y into x raised to the power of, in this case, 2 minus 1 over x minus 1. Why is it only, where did my pencil go? Why is it only y into x plus 1? Now I wrote this little explanation over here, like this little calculation, so you guys can figure it out. So the original elements formula was supposed to be this. Was it plus or minus? It was minus 1 over x minus 1. So in the place of the n, we've put 2 because we're calculating this all by 2. So y into x squared minus 1 over x minus 1. Now, as you guys know, a squared minus b squared turns into a minus b into a plus b. Now, in this case, we can write it as x squared minus 1 squared because the square of 1 is 1, so we can easily write that. That gives us our formula a squared minus b squared, which let me separate it into y into x minus 1 into x plus 1 over x minus 1. So as you can see, I cut the x minus 1 with the x minus 1, and we're left with y x plus 1, which is why we have that over here. So don't be confused if the structure doesn't look exactly the same. Over here, they've just written our answer to if we're raising it to the power of 2. Now we're going to do that exact same thing for 3. So x raised to the power of 3, the next positive integer in line. We're just going to take the answer that we got for x squared and multiply it with, we're just going to take the answer that we got for a squared and multiply it with the regular A matrix. Again, I always get confused with the plural and the singular version of matrix. No, what did happen? No, come back. No. Oh, there it is, sorry. So yeah, that's what we're doing. We've multiplied it, we've done all of our little fun stuff with it. And this is our remaining answer. As you can see, as the formula says, x raised to the power of n, and in this case our n is the number 3. And then if you further solve this, or do it like I did, you will see that it also complies to the formula that they've given, and then of course our 0 and 1. So that is the answer for x raised to the power of 3. Let me just erase that. Again, proving that no matter what positive integer we use, it is complying with the original formula that they gave us. Okay, and then this is just a simple version of a raised to the power of 1. But of course, we don't need to solve that because it's just the exact same thing. Oh, right, and see, they've shown the solution thingy here that I did before, just to explain it better. And they've done the same thing for a cubed right here. I think I keep saying x cubed and x squared. I mean to say a cubed and a squared. Yeah, they've done the exact same thing over here. They've shown you how it's possible. They've broken it down a little bit. And over here you can see in place of the n, they have 2 and 3. Okay? So I hope that makes sense to all of you. That is wrong. That should not say 2. That should say 3 as well. There's a couple of mistakes in the solution, so sorry about that. And after we've proved those 3, first of all, the x raised to the power of 1, x raised to the power of 2, and a raised to the power of 1, a raised to the power of 2, and a raised to the power of 3, we can say so on. This is just to denote so on. And then we'll just state our formula once again and say that for every positive integer n, this formula is valid. Now, part 2 is quite similar to that as well. If A is equal to this matrix, then for all positive integers n, the same formula should be used. So it's the exact same thing, it's just a little bit different. So again, they're just showing that same formula that I explained before. And of course, we have a square. Then you're just going to do a cube. And once again, you're going to state a raised to the power of 1. You can do this at the start if you want, but they've done it later. Then there's a raised to the power of 2, a raised to the power of 3, and you will say so on. They haven't done that over here. So on. That just proves that for any positive integer, this formula is valid. So it's the exact same thing as the part that I just explained. Okay, yesterday I explained how to do question 8 and 9, but after looking at the solution, I explained it a little bit wrong. I said that you could pick any 2 matrices of your choice, which I'm pretty sure you can do, but in this solution, they've decided to make the matrices themselves like this. So that's fine. If you want to do it this way, it's the exact same thing. I said that you can make your own 2 matrices of the orders 2 by 3. This one is the 2 by 3 one. And then of the order 3 by 2. This one is the 3 by 2 one. Yeah, if you want to do it that way, I'm pretty sure it can work, but I guess this is the safer side if you want to do that. All it's asking you is to consider any 2 matrices A and B of your choice with these orders respectively, and then to prove this law over here that they've shown. So you just have to prove the left-hand side, which you've done in 9th and 10th a lot. Just prove the left-hand side, find the transpose, and then do the same thing for the right-hand side. Your answer should be the exact same. So then in the end, your statement, you have to write a statement. Over here, they haven't written statements. You should write your statement as left-hand side is equal to right-hand side, A, B transpose is equal to, what was it? B transpose into A transpose is verified. You can just write your statement as simply as that. I can't write the letter D. Does not matter. Same thing for 9 over here. Again, I told you that you could do any matrix of your choice by 3 by 3 order. That's a 3 by 3 matrix. But again, they've chosen to do it this way. Again, I explained how to make these matrices back in, I think, the first video of 2.2. Yeah, exact same thing. Then you just have to prove this law over here and write the statement as similar as that. Okay? So, yeah. Now on to question number 10. Again, I've done some working here from the start so that it's easier to explain. Yesterday I was very, very unprepared, but today we're not. I know how to do things now. Sorry. Question number 10 states, if A and B are two matrices such that A into B is equal to B, and B into A is equal to A, find A squared plus B squared. Now, our solution is going to be pretty simple. We're just going to state our two givens, and then we're going to state what A squared plus B squared would equal to, which is this A into A plus B into B. And we are going to, what are we going to do? Oh yeah, we're just going to multiply each side by each other, I guess, I think. So it's just like they've added a B into the first part, and to the second part, they've added an A. You just have to write it like that. And then you can further just like simplify into a better way by writing this. They've written BA and then AB separately. You could also just write it as A into AB plus B into AB as well. BA but AB are the exact same thing. And then, of course, when you simplify that, you take AB and AB common. So AB plus your remainder, which is also AB. But again, they've written it as BA and AB, so you don't have to do that. So that is just to say that A squared plus B squared is equal to A plus B. Did I understand that? I don't think so. I really don't think so. Well. Yeah, I really don't know what just happened. Give me a second to just figure that out. I'm a terrible teacher. Give me a second. Okay, so I figured it out. Sorry, that was really dumb of me to not even look at the problem. Basically what they've done here, right? They've written that A squared plus B squared is equal to A into A plus B into B. And in our given, they said that B was equal to AB and A was equal to BA, which is again the same thing. You can just write it like that. But they just want to make things complicated, you know? So we've replaced one of the A's with BA, as you can see, because A equals BA. And then one of the B's with AB, as you can see, because B equals to AB. And then they've just switched the sides of them both together, because again, you can just write BA as AB, it's the exact same thing. So they just switched the sides to make it relevant to the associative law. And again, since AB equals B, they've put it as BA now. And since BA equals A, they've put that as AB now. Before that, they had AB, and now they've switched sides to make it BA. And before that, they had BA, but they switched sides to make it AB so that you can have BA plus AB. So yeah, that's all they wanted to do. And now, the final step. Again, we're just using our given over and over again. BA equals A, so we've just replaced it with A entirely, and then AB equals B, so we just replace it with B entirely. That's all just to prove that A squared plus B squared equals A plus B, and then all you're going to do is you're going to say if AB is equal to B, then A is an identity matrix, meaning A is equal to I, and if BA is equal to A, then B must be an identity matrix too. And you're thinking, why should it be an identity matrix? So I wrote the little explanation over here. If AB is equal to B, right, then A should be an identity matrix. I put it in like that. The ones that I've highlighted red are B, and then the singular ones are just A or AB. I've labeled them all. So A should be an identity matrix. I put A as an identity matrix. Then I put B and B. Supposedly, I just put A, B, C, D as the matrix. We are not given a B, but I just put this as an example. Now, if I calculate A times B, right? So this entire part is AB. As you can see, I've labeled that. I calculated all the multiplication, and it all comes down to equal the exact same thing as B. So AB is equal to B. That just proves that A should be an identity matrix, and that's also the same case for the BA is equal to A. You just have to switch the letters around. And then, since we've proved that A and B are both identity matrices, you can say that A squared plus B squared, which we first proved as A plus B, is now equal to identity plus identity. So we can just scribble that part out now. A squared plus B squared is equal to 2 identity matrices. I hope that made sense. This question was like really confusing and low-key kind of stupid, but yeah. Okay, now this next question is question number 11. If matrix A is equal to this, is a matrix of order 3 by 3, and the values inside use the formula I square minus J square. Check whether A is symmetric or skew symmetric. Okay, wait, but in your book it only says skew symmetric, so I guess we're just going to cut that part out. Check whether A is skew symmetric. So again, this is our matrix. यहाँ पर उन्होंने गलत लिखा था, they said B, but I just changed it to A because they're a little bit dumb. This is the formula that they were given, okay? And this is the matrix that we made. And we have to fill it with all the values using the formula. Again, we did a question like this back in the first part of 2.2, which was, the question number 1 and 2 of exercise 2.2 were the exact same things. This one is just trying to make it look complicated. We have to do the exact same thing, and we just have to find the determinant to prove whether it's skew symmetric or not. Sorry, not the determinant. We just have to use the formula, which is A is equal to negative A transpose. So yeah, we just have to prove that. So anyways, I already taught you how to make this matrix, and now you're going to just do that for each and every value. For the first value, A11, we're using I as 1 and J as 1. Again, I explained why we use these values as 1 or 2 or 3. I've even put the arrows here. I is clearly 1, that's the first digit denoting I, and J is 2, which is the second digit denoting J. So we're going to input those two values into equation number 1. I've labeled this as equation number 1 because this solution that I have downloaded is a little bit like vague about what they're doing, so I've just added these extra statements, which you should also write in your exams or in your notebooks or whatever, just to make things easier to understand, and they also get you marks. So we've done this for every single value. We did A11 first, and we did A12, then we did A13, all the way down to A33. As you can see here, I've labeled each and every one. I'm just going to go a little bit slow so that if you want to pause it and check it out, you can pause it. They've just inputted everything into the formula and found the value, okay, which we're going to put into our matrix right here according to the values that we found. And now we just have to prove whether it is skew symmetric. So the formula for a skew symmetric matrix is this. So what we're going to do is we're first going to find the transpose, and then we're just going to multiply it with the negative, okay? So it's just going to be the negative transpose of the matrix. And as you can see over here, I wrote it as skew symmetric but not symmetric, but in your book it's only asking for skew symmetric, so I guess you don't need to really write that that statement. All you have to do in the end is just write that A is skew symmetric, proved. Now for question number 10, for any square matrix A, prove that A raised to the power of n being any positive integer, whole transpose is equal to A transpose raised to the power of n. What we're going to do in this is we're just going to take our left-hand side, which is this part of the formula. We're going to take our left-hand side, which is this part of the formula, and we're first of all going to say that, okay, now the reason we've done this as many times as possible and we've put that so on place is just to show n. N means any number or like any positive integer. So we're just doing it we're multiplying it as many times as we can and then saying so on just to show that it's any number of positive integers, whole transpose. As you can see, we put the transpose outside the bracket. That's what we've written over here. And now since it's whole transpose, we can put transpose on each and every matrix of A, right? Again, we're showing so on to say that it's as many number of times. Okay, we can put the transpose separately, and we can even now put it in a bracket, because if I wrote a raised to the power of 2, suppose n is equal to 2, right? I wrote a raised to the power of 2 whole transpose. I can also write it as a transpose into a transpose, right, as they've written over here. And if it was raised to the power of 3, if n was equal to 3, then I can write that as a transpose into a transpose into a transpose. So that's what we've done. Again, so on to show that it's n number of times, meaning as many positive integers as we have. And since that directly just shows this, if I wanted to make a closed version of this part, I would write it as a transpose raised to the power of 3, which is what they've written over here, which is exactly equal to the right hand side that we've done. This is just like to show a little law, I guess, to prove the law. And this one is quite an important question as well, so you should make sure to memorize this one. And if it doesn't make sense, you can just ask me again and I'll try and explain it. So that's what we've done right there. Now, question number 13, which is the last one of this exercise, I believe. Find the matrices x and y such that 2x minus y is equal to this matrix and x plus 3y is equal to this matrix. Now, I think from 7th grade, you all will have learned the method that we're about to use, where you have like one equation, and then you have the second equation, and you times one of them by a number to, like, subtract it from the second one. So that's basically what we're doing. I hope that made sense, but this is a very common method, and you're gonna know what I'm talking about as soon as we look at the solution. So these are two given, which they have labeled respectively as 1 and 2. Okay, the 2 is very far away, but you understand. Now we're gonna multiply the second equation by 2. And why are we multiplying it by 2? What we want to do is we have to find x and y matrices separately, right? So I want to cancel out at least x or y, one of the two, so that I can find the other one. In this case, I can multiply this, I can multiply this, stop, what is going on? That's not very nice, that's not very nice. Sorry, let me just fix that. There. I can multiply the second equation by 2 so that it's 2x, alright? Obviously, all the other values would also change, but this would become 2x. And since it's 2x, when I subtract it from here, the 2x and the 2x will cancel out, which will just leave me with the y components, and that'll allow me to find the matrix y. You could do it the other way around as well, where you just multiply the first equation by 3, so that it's 3y, and you can, cancel them out from each other. But it's better to just do it this way. Actually, wait, no, you couldn't, because the signs are already opposite. This one is plus 3y, and that one would become minus 3y, which would not work. The signs have to be the same while you're doing it. So it's become positive 2x, and you obviously minus 1. So multiplying the second equation with 2, we've just had the entire second equation on the inside, and then we have our 2 that we're multiplying it with. That's what we've done over here. We've done it on both sides. A better way to have written this was this 2x plus 3y with 2, and then the entire matrix, whatever it says. Multiplying 2 with equation number 2. You should say multiplying 2 with both sides, BS, both sides of equation number 2. Okay? After we've done that, this is our end result, and we are going to name this equation number 3. Now we're going to subtract equation number 3 from equation number 1. That was the entire point. And we have subtracted both sides from each other. This is the one from equation number 1, and this is the one from equation number 3. This is again from 1, and this is from 3. After subtracting it, you can see that 2x and 2x canceled out with each other. It's negative, that one's positive. Minus y and minus 6y. Minus into minus is minus, but it's a plus operation. So minus 7y. Then you do the working of your matrices, and you are left with this. Okay? Now, after you're left with that, we have to find out y matrix separately, right? So we are just going to take this minus 7 and throw it onto the other side. Now, I explained this before as well. Right here, they're writing it as 1 over minus 7 into the matrix. But I prefer to just directly divide it. So what I would have done was Oopsies. Sorry. What I would have done would be this. -7. I'm very bad at writing. -7 over -7. 0 over -7. -7 over -7. Once again, stop doing that. Over... This is actually like getting on my nerves. That's not funny. That's actually not funny. Let me just get back to where I was. Sorry. Over another -7, and then 0 over -7. 7 over -7, and then 7 over -7. Okay, that's our entire matrix, and then I would solve that separately to become 1, 0, 1, 0, -1, and -1. But if you want to do it the way that they've shown in the solution, you can do that too. I find it easier to just divide that by each of the values. So it'd be like this, and then you would divide it with each of the values. And after you've done that, you have found matrix Y over here. See, they just do this extra step for no reason. You can just easily divide it without having to do that. Then you just find the matrix Y, and using that matrix Y, you can put it into either one of your formulas, 1 or 2. They've put it into 2 over here. This was 3Y, but they've just replaced the Y value, and here's our 3. And of course you just solve that, you multiply this entire thing by 3, which becomes this, then you take this onto the other side, and it subtracts, and that leaves you with your X matrix. So, yeah, that's the end of exercise 2.2. It was a lot easier than the first few questions, because I feel like after you've practiced the first few questions, you will get the rest of the exercise very, very easily. And yeah, that's it, guys. Have fun with your lives. I'm gonna put out a video for 2.3, hopefully tomorrow, I hope. And, yeah, just have a great life, guys. No, I'm not gonna do that, I'm sorry.